Probably you have seen on the KLMS, I updated the syllabus. I added a lot of more materials, okay, more topics. Because our class is a little bit special because we have both quantum science and technology graduate students and EE people. So I try to make it like helpful for like both departments. All right. So kind of what's it, interdisciplinary. So if you can look if you look at syllabus, it has both like a little bit of a solid state physics and AMO physics, quantum computing. So then after I write that, realize we need to rush. Okay, so I'll go a little bit quick. Right, so let's continue. We were doing this complex math thing. But don't get too scared, all right? It's just an exponentiation. It's a Taylor series, except that you put operator on exponent, and then it is defined, okay, defined as a Taylor series. All right. So we just like carry out, you just follow the definition and see our previously studied rules are working fine, and then it doesn't like give you wrong results. So far it was all okay. So let's continue. So I was telling you that this unitary operator, you can actually write in the form of the time evolution, right? Actually write in that like polynomial form. And then if you apply that to energy eigenstate, Hamiltonian will extract, right? Extract just the energy number, right? And then the quantum state is staying there. So we apply it to the ground state. And then from here, you can observe that. So our original condition for normalization at time t equals 0, it tells us that it needs to be 1, right? The length square has to be 1 to apply Born rule interpretation. And then after some time evolution, so you will have this function instead, right? There is some time passed. And then this length also needs to be 1, right? So if you look at this expression, so calculating that is nothing but taking bracket for the spatial part, and then time-dependent part is what? It's just this, right? But exponential I theta shape is just the 1, right? So you confirm that your energy eigenstate after some time evolution, it is still keeping the same number as 1, right? So its normalization condition is working all the time for an energy eigenstate. Okay, that's a simple example. I'll expand it to more complex scenarios where, okay, what if your quantum state is an arbitrary one at time 0, right? So it's a linear combination of these bases, right? So it's a energy eigenstate, for example, something like particle in a box. It's a complete basis. So any quantum state, you can expand it to that basis, like this linear combination. And then this one, after some time evolution, what's going to happen? Let's see, time evolution. So this one will become, we already know the answer, right? So it will have this time evolution phase term, right? And then each energy eigenstate will have a different speed of the phase evolution. All right. So that's what we have learned previously. And then now what we're going to do is to do the same thing as above to this new like arbitrary state. All right. So the math becomes a bit complicated, but it's not a big deal. We can do it. So this unitary operator, right? You propagate in time, and then you apply it to the initial state at time t equals 0. What do you have? Basically, you are doing this thing. Okay, this row, right? This thing to each term, right? So actually, it's nothing different, but for this index, right? There are many, many infinite terms, but that infinite terms, they all look like this, except for the index. So that's what I'm going to write. there's a sigma sign there. Ci is staying the same, and then you will have, what is that? It's I square h bar square ei square and so on, right? And then there will be psi I, right? It's the exact same thing as we've done like up there. And then this expansion here, right, in parentheses is what exponential term, right? Exponential minus IEI over h bar t, right? This is exponential expression. And then we recover our usual result, right? Okay. So, but like basically like, I'm doing this, arriving at the same conclusion for two different paths, right? The previous one I wrote up there, if you remember, that was the result of like solving time-dependent Schrödinger equation with the separation of variable, right? There was an assumption that V is not a function of times these things, right? And then you can do that, right? You can get that solution by just solving math. But this time I've done a little bit different approach. What was it? It was, again, we started from the, one second, where was it? Yeah, again, we started from the time-dependent Schrödinger equation, but then we actually took this, started from here, right? So the change is a time evolution. It's an operator applied to initial state, and then you put it in the equation, and then we got this differential form of an operator, right? And then I suggested, well, actually, this form defined as here is a solution to that, right? It's a bit different approach, right? Different approach from what from the beginning. In the first few weeks, right, we really just solved the math problem like straightforward. This time we went a little bit more abstract, right? We like introduced this exotic thing like differential equation of an operator, but like actually that can be solved. So that method we're applying here, and then we arrive, of course, we should arrive at the same result. And then let's check this one again. The normalization condition. So it needs to be 1, right? So previously we know that if we do the calculation, it's going to be the coefficient absolute square addition, right? Summation, that's going to be 1. And then after time evolution, so this one, length square is going to be the coefficient. You can interpret it as, oh, well, coefficient gained the phase, okay? Over time gain. Coefficient gained the phase. That's just all about it. It's just a simple interpretation. So instead of CI is being a coefficient, now your coefficient is what? CI times e to the minus c I e I h bar t, right? So do that. That exponential doesn't do anything because it's just 1. What? We confirm that the length square is being kept as 1. And then for arbitrary quantum state, it's like this. So we know that this ut is indeed, right, this one is a unitary transformation. It's always keeping the length the same. Okay, that's a unitary transformation. Okay, so that exotic operator exponentiation was a unitary transformation, okay? That operator was a Hamiltonian. And now let's move on to another type of an operator called Hermitian operator. In quantum mechanics, these two are most important like types of an operator, okay? Hermitian and the unitary. So Hermitian, I think I've mentioned, so by definition, it's defined as this. If you take the complex conjugate, it becomes itself, okay? Unitary was its inverse. This one is itself. So to give you more concrete idea, let's say we have this 2 by 2 matrix. This one is what? U, this transpose, and take complex conjugate, right? And then this is supposed to be the same as just M. That's condition for Hermitian operator. And then this is important theorem that physical observable. Okay, what something you can measure? Okay, something you can measure are represented by these. By Hermitian operators. Okay, so give you an example. These operators we have learned, right? The multiplying x, I told you it's an x operator, position operator. P was what? In quantum mechanics, this differentiation was representing P, right? And then energy was represented by Hermitian operator, an Hamiltonian operator, right? And these all three, right? Position, momentum, energy, these things are all measurable physical thing, right? Physical quantity. So they are all supposed to be Hermitian operators. Let me give you an example of an expectation value of an operator, and then you will see why physical observables need to correspond to Hermitian operators. So let's see, there is an operator Q, and we're calculating expectation value of it for a given quantum state psi. So you're evaluating this basically, right? This sandwich bracket form. And then, okay, so like, so bracket is nice, but it's always somewhat abstract. So let's be a little bit, become down to earth, and then think about, okay, if I write that down as a matrix, what is its form, right? It's always helpful to do it. Let's do it in matrix dimensions. Okay, how big is these? So let's say assume that we're working with for n-dimensional Hilbert space. Basically, the number of elements in your basis set is n. Then this calculation is getting which way? So the bra is a row matrix, right? So it's going to be 1 by n. And then Q is n by n, it's an operator, right? And then the cat is a column matrix, so it's going to be a n row with the one column, so n by 1. So as at the end of this calculation, so as you expected, it'll give you just the 1 by 1, just a number, okay? That's what you would expect if you take the expectation value of like some operator, so you get number. And then this number, right? Let's say, okay, this is nothing but just a complex number. This complex number, I would like to take a complex conjugate, okay? So this one, since it's just a number, right? Actually, you can write it as complex transpose, and actually it works as well. Because it's just number, you can also think of it as a 1 by 1 matrix, right? Yeah, so it's just a transpose doesn't happen because it's just the one. But anyways, you can interchange between this star and then dagger, right? For a number. And then, okay, for this dagger, let's go back to our original expression. What you're doing is you're applying dagger to this bracket, sandwich bracket form, right? And then we have learned how to apply the rule to these cascaded matrices, right? If you put dagger, you swap its orders and then apply dagger to each of them. And then what is that? Cat becomes bra, Q becomes Q dagger, and then what is that? Bra becomes cat and it comes in the latest, right? So you actually get this. All right. So let's say, so something measurable, right? Something measurable means that, okay, the operator corresponding to something measurable, if you take the expectation value of it, it's going to become a real number, okay? Because whatever you measure something, it gives you a number, right? Real number. So for the real, getting real Q means that it's a measurable quantity. Okay, so for that case, right? For real number, you take the complex conjugate here, right? For a real number, you take that, actually it doesn't do anything, so it's going to be the same, right? It's going to be this. And then, what is that? It was this. Now you see why the Hermitian and these two being the same, right? These two being the same, why it's linked with the real number argument and the measurable quantity argument. Because for Hermitian, these are the same, right? They are the same. And then that actually means that this is a real number. Okay, expectation value became a real number when you have a Hermitian operator. Let's keep looking at the details of a Hermitian operator. Now I'm going to look at its eigenstate, okay, eigenvalues, eigenvalue, one sec, eigenvalue, of Hermitian operator. We just saw expectation value, but this time let's look at its Hermitian operator's eigenvalue, okay, if they are real as well. So let's say we have this M operator applied to quantum state, and then eigenvalue problem form, right? There's eigenvalue and eigenstate, and then this is normalized, okay? Normalized quantum state, remember that, as usual. Okay, and then what I'm going to do is I'm going to calculate psi n m operator sandwiched. What I'm doing now is that I am actually doing what? Applying m to eigenstate, okay, eigenstate. You apply your operator to the right-hand side, cat is going to give you just this number, eigenvalue. And you sandwich the number there. So this number can just escape bracket. And then you have this, the length square. Length square is supposed to be 1 since it's normalized. So you just get mu n, okay? And then we'll do the same thing as the previous slide. So for this one, psi n m psi n, it gives you this number. So for this number, I'm taking, right? So this number was mu n, right? And then for this number, if you take the complex conjugate, psi n, m, sorry, it's, okay, n is supposed to be dagger, right? So I did that thing again, yeah. Apply the complex conjugate, the m is there, and then what do you get? So since it's Hermitian, the m dagger can be gone, right? Just I leave m, right? So it is just the mu n, but actually originally we started from mu n's complex conjugate, right? So complex conjugate in itself is the same. So we get a conclusion mu n is real. Okay, Hermitian operators eigenvalue is supposed to be real. So this one, your eigenvalue is going to become a real number. Actually, you can prove in both ways. So actually, if and only if. All right, and then next one, eigenfunctions of Hermitian operator different eigenvalues. So I'm going to discuss two eigenfunctions, and they are both eigenfunctions, but their eigenvalues are not the same number, okay? So that one, the problem description is m psi n, you get mu n psi n, and m psi m, you get mu m psi m, okay? And then these two numbers are different, I'm saying. So this is our assumption, this condition, okay? From this assumption, what conclusion we can extract? Let's go here. I'll take the sandwich of this expression, and then it looks a bit odd, but I'll write down something trivial and obvious. Okay, I'm just subtracting a from a, so it's supposed to be 0, but here you will see the usefulness of the bracket notation and formalism. Since what I'm going to do is, okay, let me write down again to make things clear. Same thing, I'm subtracting. And then, so you are allowed to calculate when you multiply ABC matrix, you can do AB and C or A and BC, right? You're allowed, so you'll do this separate calculation. You change the order. It's okay. So the first one, so let's be a little bit more explicit this time. So that one, I am allowed to write it as M psi n complex conjugate, right? That parenthesis part, I'm allowed to write that way. And then, okay, here, minus psi n, and then on the right-hand side, that one, to make it clear, I'll use this color m psi m, right? So this one here, right? So for this step, I'm going to use the fact that this is Hermitian. So m dagger, I'll just write it as m, right? Because it's Hermitian, I can do it. Minus this one, I don't just still keep it this way, m psi m. Okay. So the next step, right? This, you apply your operator to an eigenvector, you'll just extract the eigenvalue, right? So it's going to give you this mu n will come out, right? Mu n will come out. Mu n will come out, and then psi n is left with the dagger, so you can turn it into bra. And then the second term is simple, right? You apply m to the psi m, you just extract mu m, right? So mu m psi n psi m, right? So it's a very simple, nice algebra. we started from something obvious, but actually you arrived here. By applying M to left and right separately, you actually take out the number is different. For first term, first way you extract mu n, second way you extract mu m, right? It was possible because it was Hermitian. And then you get this result, and then I told you they are not the same number, right? Mu n, mu m are not the same. So you can have this conclusion that they're orthogonal, because their eigenvalues are orthogonal. So for a given Hermitian operator, you have these eigenvalues, okay, eigenvectors, and different eigenvalues. They have to be orthogonal, okay? And then I won't give you the what is the proof, but people figured out that if you do really rigorous calculation, it is possible to show that they are actually complete. Complete, right? You can expand any arbitrary quantum state into eigenstates of this Hermitian operator for most cases. To be accurate, okay. There are some cases this doesn't work, but most of cases it works. Mathematically, you can prove it. And okay, we discussed Hermitian operator, and then before Hermitian, we discussed unitary. And then let's make connection between them. It's quite very, very interesting. Their connection, Hermitian and unitary. So we will start from again this e to the I theta, the Taylor expansion, 1 plus I theta minus theta square 2. And so on, right? That was cosine theta plus I sine theta. Okay, so I just wrote that as a reference, and then we will evaluate this expression. Okay, so this u, I'm not assuming it's unitary yet. You will see it's unitary soon when this M is Hermitian operator. Basically, we want to show that if you exponentiate Hermitian operator, you will get another operator that's going to be unitary. All right, so let's do how this works. So we learned it, right? This is how you exponentiate an operator. So on, right? And you will evaluate, 1 second. What I'm going to calculate is U dagger, okay? U dagger e to the I theta m operators Hermitian conjugate, okay? So this is not difficult. You can just try Hermitian conjugate to all the terms. And so on, okay? So, of course, right, we assume that M is Hermitian, so it's time to apply that fact. The dagger can be all gone. And then you realize, right, you actually can write this as what? E to the minus I theta m. Right. By definition, it is e to the minus I theta m. Okay, so in just a number, right? When you calculate just the complex function, it's you have this, and then you can do the same thing for this case. Okay. So well, the one caveat is actually you cannot just whatever like treat the more operator exponent like usually what is that if you have that shape you usually for number you can just remove e and then just add them up, right? So what is that? I think in operator you have to be a little bit more careful, right? Because they're commutation relationship. But anyways, this case is doable. It's doable, and then you'll get just an identity matrix, and then you realize that this U dagger multiplication is just the identity matrix. Okay. So our conclusion is U E I theta M is unitary when M is Hermitian. So if you exponentiate M Hermitian in that form with the I applied to it, then actually that result, right, resulting operator becomes unitary. And then actually the opposite direction also for unitary. So there is a given unitary operator, right? There is a Hermitian, okay? There is some Hermitian. For some Hermitian, it is possible to use this expression, okay? So it exists, M exists that allows you to express U as an exponentiation. So that's a mathematical result. I didn't give you proof, but like the proof is in the, it's just too complicated. I omitted here, but that's a conclusion. It's that relationship, okay? Exponentiate Hermitian, you get U, okay? For a given U, you can always find that such an M. So the example of such a thing, the most prominent example is what? We have learned, right? Time propagator and the Hamiltonian. Hamiltonian is corresponding to energy, so actually it's Hermitian, right? So that theta, I'll write it as this, okay? Then you'll feel more familiar. So basically, I substituted theta for minus t over h bar, okay? And then you're exponentiating your Hamiltonian with some numbers multiplied to it, right? Of course, it has to be what is it, I. And then you get this U, which is unitary, and then you get unitary transformation. UT, which is the time propagator, okay? Time 0, and then you get time t, okay? So that's actually, you can see it as an exponentiation of a Hamiltonian operator. Okay.
Recording stopped.
Okay, sorry, internet somehow stopped working, but
Recording
we
in
can continue
progress.
now. Okay, so it's back. It's like, hmm, why is it like this? Uh, So I am going to use a PowerPoint slide for like next 20 minutes for today, and then explain things about spin. Okay. So one sec. Not this one. One second. This is not what I want. Okay, let's do again. Okay, let's do it this way. Somehow it's mirroring, but it's okay. All right, so hmm, oh sorry, something's wrong about it. Okay, and then zoom. Okay, as I want, share desktop too. Okay, okay, better. Exactly as I want. So I prepared the slides not as a lecture note writing, because I kind of like to explain things, okay, qualitatively as much as possible first, and you actually know the thing, all right? Know what that thing is, and then you do the math. I think it's better because it's very easy to get just swallowed by the math if you just like jump into the math. All right, so let's just look at the thing, okay? How people found out electron spin. So we'll move on to the next subject, spin, okay? So spin is a realistic subject, and also it's quite nice because, especially these days, because it's really similar to quantum computers, qubits. Qubit is actually just a spin, all right, exactly the same. So we will learn how spin, and there is this historically famous experiment called the Stern-Gell experiment. It's name of two people. They did the experiment together. So throughout this experiment, they found out there is a thing called the spin, okay? And then, so from this name, right? So actually this name is a little bit misleading because spin, you actually think something is rotating. One second. There was a chat from student. Oh, okay. The student said the audio is not working. But actually looks fine from my side. I don't know. Maybe you should check your, if he doesn't hear. Okay, yeah, another student replied. All right, so let's continue. Audio is working. It's working. Yeah, so my microphone is working. So if it doesn't, you can't. Yeah, there's a possibility the speaker is wrong. Anyways, let me continue. So Right, the spin is a little misleading because you think the electron is actually spinning like a ball, but actually not, okay? There's no such thing. But it's a good metaphor because if you have something like that, right, some charged particle spinning, and then charge is somewhat like spread over this ball, then actually it will produce what? Magnetic field, right? In that sense, it's kind of a good name, but actually it's not really spinning. So electron spin, simply speaking, you can think of it as okay, it's a small magnet. Electron is like you usually learn it as a charged particle, but actually it's also a magnet. Okay, it's like a magnet, but it's a different from classical magnet, and we'll see the details of that structure throughout this experiment and math. But let's look at the experiment first. So it all starts from the Niels Bohr, Bohr model. Bohr model is like it's so important, so it's included in high school physics. So basically, he claimed that electron orbitals are quantized. Okay, he said quantized, and then he did all this calculation, and he assumed that electrons are actually jumping between these like fixed orbitals, all right? So rather than there is a continuous possibility of like location. He said, okay, these orbitals are some discrete things, and then whenever you jump between these things, you observe or emit light. And then, so it turned out that the way he calculated is that angular momentum of this, right? Because it's an orbit, right? You can calculate the angular momentum. These numbers are quantized, okay? Multiplied by n, okay, this natural number n is called principal quantum number. Basically, when you learn orbital from chemistry class 1, 2, 3, right, these numbers, so like, the shell of the electron, right? So that's this principal quantum number. And then actually that number, right, is kind of there was another famous scientist at the same time called Sommerfeld. He tried to extend this model further, right? Because that's n number is not enough to explain everything. And then the another quantization he tried to use was this thing called the what is that, elliptical like model, right? So he assumed that, oh well, that orbital maybe doesn't look like circle, rather it's an ellipse, and then how much it squeezed actually can be quantized. That's what Sommerfeld assumed. And then he called it this azimuthal quantum number. I actually didn't call it, but like this thinking is wrong. Actually, it's wrong, but it has it gave you a good clue. Okay, it gave you a good clue to lead to an accurate azimuthal quantum number L. Okay, so this is called a directional quantization. All right. So this is like what you see like from s orbital, p orbital, these things, they have different L numbers, right? So that's another quantization number. And then, so there it is. It's a historical development, okay? It's a story. So some other scientists thought, okay, that doesn't look quite right. They were not really believing in that ellipsoid number, okay? Quantization of the ellipse. And then these two numbers are Stern and Gerlach. Okay, they did not agree with this directional quantization. So they wanted to do experiment, okay, to see what's really correct. So they didn't really believe that claim, the theory. So then he like talked to many other scientists, and a lot of scientists actually like supported them. Okay, their thinking may be correct. So they, including Einstein, they set up an experiment. So at that time, right, they knew that these atoms are like little mini magnets. So they respond to like magnetic field. They knew that already, right? But they didn't know all these like, all these detailed structures like we know now. So they planned the experiment, all right? So they thought, okay, this electron has some directionality, like something like has this shape and that shape. They will, because their orbits are different, right? And then they thought, okay, they will give you different magnetic field, okay, different magnetic moment. So if you remember from electromagnetic, like one of very important topics is what? Electric dipole and magnetic dipole. Okay, magnetic dipole, electric dipole is what? Plus minus, same charge, plus Q minus, separated by D. All right, dipole is QD. And then magnetic dipole moment is what? Closed loops, like closed loop, it can be circular or whatever shape. The current is flowing, right? And then you multiply I and area, then you get magnetic dipole moment. All right. And then you can easily think, okay, maybe there is if your orbital is different, basically it means that you're like classically thinking your loop is in different shape or size or whatever. They're somewhat different. And then if they're quantized, they will give you some different magnetic field. So let's explore it. Okay, that's what they thought. So they set up an experiment. It's really, really nice experiment. So they have an oven. This is very hot, and then like you can boil something, and then you can actually like spit out one by one silver atoms at the time. Okay, they spit out silver atoms at the same time, and then of course, right, it just goes everywhere if you have such a thing, because it's a hot, and then it's just bouncing around in all random directions, right? It's going to be random. And then, but there is a way you can make it very, very directional. How do? You have this box of boiling silvers, and then you make a small hole, they will get out, spread over in different angles. You can put some slits like that, and then you can make it very, very directional like a laser, all right? So you shoot a straight line of a silver atoms going fast, and then you put that special magnet, right? So you can see that N and S, their shape is kind of weird. It's intentional, okay? It's intentional. And then they measured silver atom is arriving where by putting a screen there, okay? And this experiment, so the reason they do was that basically you see that magnetic field pattern, right? So actually they intentionally introduced magnetic field gradient along the height, okay? So stronger magnetic field near S, that sharp tip, right? Because the field lines are dense, and then bottom it's like weaker, right? The direction is like that. Anyways, you have a gradient. And then if you have a gradient, actually, you can figure out magnetic dipole moment, its direction and strength. So that's the experiment they set up. And then what they expected was that it's something like this. So on the screen, right, they actually expected something like some continuous, like smooth, like lump, okay, like data. The atoms are arriving in like some sort of like, Gaussian profile, whatever, continuous one. But actually, they have seen very clear islands, and then there's nothing in the middle. Okay, that was the surprise. That was the surprise of the experiment. It's a historically important experiment. And then magnet's orientation, right? Basically, it is showing up as the location of the arrival, okay, along the height axis, okay? So, one second, let me. The issue is that it showed the quantization, all right? So the quantization was a surprise finding. It's a original real data of the Stern-Gerlach experiment. You can see that there is this like white part, right? There's nothing. So this dark area means that these silvers have arrived, okay? The silvers have arrived. You can see that there is a clear, this is data, okay, I'm talking about. It's a clear distinction of the two lines. And then they actually, if you interpret it right, they actually correspond to this and that. You can see that, right? They're flipped, okay, up and down. So if they're flipped like that, you will get that. But then why do they expect something in the middle is like not like, this like distinct islands? They would rather expect a spread, because if things are randomly coming out, right, the magnet is not going to be like this, right? Magnet is not going to be pointing up or down. It's going to be a continuous spread, right? So that's why it was a surprise. And then actually So if you give me more details, this experiment is not really what you really intended. Actually, their experiment was actually, they misunderstood at the time. This is a science, okay? You don't have to be 100% correct. You need to be reasonably correct. Reasonable assumption, reasonable setup of experiment, reasonable explanation. Let it reviewed by peer scientist, okay? And then, and then as long as it's logical, like reasonable assumption and logical development, and then every single word in your paper doesn't have to be all correct, okay? You can say that it looks like this. I think this way. Probably this is true. Maybe you can try this further. Paper is like that, okay? It's not 100% true. So this was actually the case. It wasn't 100% true because Stern-Gerlach experiment, when they were doing experiment, they thought atom is a magnet, and that magnet, right, coming from electron is spinning around, not like orbital momentum is giving that, okay? They thought electron is something like moving around the core, and then this is a current loop, and then that will give you a magnet, okay? That's what they assumed in the beginning because they thought so because they didn't fully understand silver atom at the time. Now we fully understand, but at the time they didn't fully understand. So they thought, well, this a silver atom is like a magnet, and then origin of that magnetic behavior is coming from like electron going orbit around. That's how they assumed, but actually not true. Later, people figured out that silver electron, right? So what's giving you that magnet is actually that outermost shell's electron. Okay, there's a single electron. Okay, if you study chemistry, actually you learn like the silver needs to be like that. So it fills up all the shells, and then there is a one leftover electron, and all the filled shells, they don't give you anything, any magnet. But the leftover one, that one electron itself, will give you this magnetic dipole moment. But it turns out that silver's orbit, right, doesn't have angular momentum. Okay, so actually there needs to be something more to give you a angular momentum, okay, the spin. Basically, I'm mixing the words angular momentum and like magnetic moment together because we're talking about charged particles angular momentum. Charged particle has an angular momentum. It's going to give you what? Magnetic moment, right? It's a current loop. All right. So that I'm mixing these two expressions, but they kind of the same thing if you have a charged particle. All right. So there was a problem. So and then they thought, okay, oh, there's something needs to be figured out because obviously by experiment looks like there is an discrete angular momentum, right? But actually it's not coming from the orbit. Orbital angular momentum is zero. There is something else. What is that? That's spin. Electron itself is like a magnet. And then they are discrete. So that's their finding, okay? There are two allowed electron directions, okay, for electron spin, right? So they thought, okay, electron orbital is not giving you anything, but still it's behaving like a magnet. It's a charged particle. Then what kind of rotation is happening? They thought, okay, maybe just like think of it as the electron is spinning like this, okay? Then classical picture, actually it makes sense that it's giving you a magnet. All right, so, but the electron itself is not really spinning, okay? It's just a metaphor. So to give you a orbital angular momentum, spin angular momentum metaphor, the solar system is the best example. The Earth is going around the sun, right? Like this, that's an orbital angular momentum. But at the same time, we have night and day, 24-hour period. That's this spinning, right? Revolution of the Earth is like a spin. The same thing, an atom, nucleus, right? Electron, you can think of it as going around, it's orbital, and then it itself is spinning, that's a spin, okay? So in case of electron, right, the spin, right, so like the difference between electron case and the Earth case is that in the end, right, for example, the classical mechanics, the Earth's motion, right, they're kind of the same thing. in a sense that it's all about this atom moving around. Okay, the Earth spinning, the atoms are just moving around, right? With this axis or that big axis, all together happening at the same time. So it's actually the same thing, same model. Okay, in the end, they're the same thing. But electron's case is somewhat different. Electron, orbital angular momentum is coming from the fact that electron is spread over in space. Okay, it has a space coordinate. So that's the origin of the orbital angular momentum, but spin itself has nothing to do with that. Electron, you assume electron is a like size, there's no size for electron, okay? But still it has a spin, okay? It has nothing to do with like spatial behavior. So somewhat you can say it's a fundamentally different orbital angular momentum of the spin electron and spin are two different things. But in the end, you will learn they both produce magnetic field, okay? And then there is a rule for combining them. They contribute both, okay? There are two mechanisms for electron producing B field. Okay, so let me give you a quick review. Electron, what is that? This is what you learn from electromagnetics, right? Electric dipole moment is QD, right? Separated. In case of magnetic dipole moment, there's no magnetic monopole. There is no such thing. You can make an island of N, right? North and south pole separate. You cannot separate. You cut your magnet. You can keep cutting, but it will never give you N alone, right? So then instead, your magnetic dipole always you should think of it as a current loop. Okay, current loop. And this current loop is a magnetic dipole, and then as the name suggests, right, the field pattern they produce is exactly the same. Okay, the dipoles, electric dipole, magnetic dipole, although they look different, but far field, if you move far away, very far away, okay, compared to the size of that dipole, right, the D or the loop size, if you move very far away from these two dipoles, the field pattern for E, okay, electric field produced by electric dipole, magnetic field B produced by that loop, they are mathematically the same. Okay, as the name suggests, they are the same. They're both dipoles. So, so as I mentioned, right, if this one, right, the charged particle is moving, the current is charged particle moving, turning around all over, right? So there are two quantities. One thing is the magnetic dipole moment, right? The other thing is also as a particle's mechanical motion, you can see it as an angular momentum, right? So this is angular momentum is producing the magnetic dipole moment. That's an angular, what is that, orbital, basically like orbital angular momentum electron is produced this way, but spin is like not, okay? And the magnetic dipole moment, the current loop you can put inside the magnetic field. I'm trying to explain how Stern-Gala experiment worked because you are throwing the magnet to the magnetic field, okay? And then it'll feel the force, right? So basically, we're throwing in the current loop, basically, okay? Current loop is a magnetic dipole moment. It's a magnet. You're throwing in the current loop, magnetic dipole moment into the magnetic field. It's going to feel the force, okay? So when they're, what is that? So for both electric field and magnetic field, it's a classical electromagnetics. We're just reviewing, okay? So you can read your textbook if you don't remember. You throw in your dipole, electric dipole in electric field, it'll feel the force. You'll throw in your magnetic dipole in magnetic field, it'll feel the force, okay? Sometimes it's just like push, sometimes it's just a torque, okay? And then their potential energy is expressed as what is the minus inner product of a dipole moment and the external field. Okay, so these expressions you can actually calculate. You can deduce from electromagnetic theory. So what happens is that the force is what, if you have a potential energy, if you take the gradient of it, right, you feel you have a force, right? So that's what happened. That's how you designed the force for the Stern-Gala experiment. You produce this like B field environment, right? Then if you have this B field environment non-uniform, then you take the gradient of this inner product, okay? For a given magnet, you put it inside the magnetic field. That inner product, if you take the inner product of this B field, if you have this B field is like not uniform, it has a gradient, then you actually take the gradient is non-zero, right? Then what is that? You will feel the force, okay? That's how they designed the different magnets will feel different force, okay? As you can see, right? The magnet's direction is included in that information, mu vector, right? Magnetic dipole moment vector. Okay, that actually give you information of n is pointing where, how strong it is, right? It has all that. So that's how they design. So this is what I explained. I'll repeat again. They thought the silver atoms, the magnetic dipole moment vector will be like that random arrows. And then that random arrows, if you do that calculation, okay, like what is that, the gradient of a mu dot b, if you do the calculation of that random thing, you will have this lump in theory, but actually in experiment, you didn't. So you only have to conclude that somehow that electrons magnet is only this like digital, okay, up and down. Only those two are allowed. It's very, very surprising. So they call it spin, okay? They figured out, okay, it cannot be an orbital. Okay, there is something else. Let's call it spin, okay? So then in classical mechanics, right? If you have some size of a particle spinning around, actually you probably learned it from the first year physics, right? You can, if you have some mass spinning around, you can think of it as a little like the ring is a spinning around and you can just integrate, right? It's a collection of all the rings actually, or all the disk if you have a thing inside. It's a field inside, you can think of it as a collection of disk, but each collection of disk also a collection of rings, right? So in the end, these rings are like going around, and then from the particle's point of view, within this ring, it's actually its own rotation, right? So in that sense, classically, this was that revolving, and then the rotation of the Earth are the same. But for electron, right, you cannot think that way. Okay, you cannot think that way. But it's a metaphor. Okay, it's a metaphor. If you have a ball charged and it's spinning around, then classical calculation is going to, because you have a lot of little current loops all collected together. So it's a metaphor, but it's not really the case. And then, okay, so back to silver atom Stern-Gerlach experiment development. Let me explain. So since they were assuming orbital angular momentum, they assumed the spin is plus minus 1, which will also allow the plus spin 0 in the middle, but actually that wasn't the case, okay? There were only two possibilities. There were not three lines, there were two lines, okay? Then spin plus, actually, it was spin half, okay? Spin plus minus half. So then this experiment was done in 25. It was reported, but it wasn't super clearly explained until 27. And then there's another physicist, Ralph Kronig. He came up with a spin argument. Okay, he thought, okay, it cannot be an orbital. It should be a spin. He came up with this idea, and then he was discussing with another physicist, Wolfgang Pauli exclusion principles Pauli, and the Pauli said, "Oh, that looks like it's not complete. Don't publish." Then he didn't publish. But later, another scientist, these two people, I don't know how to pronounce their name correctly, but anyways, these two people, they published the idea, and then another famous physicist, Ehrenfest, he supported it, and then they took the credit, who was first suggested this spin idea, but actually historically, Kronig discussed, he just didn't publish, okay? But it's just a story, became a story, there's no paper. Anyways, it was a suggestion of a spin idea, okay, not full explanation of how these things work, why it's spin half, all these things. Had to wait until 1927. Wolfgang Pauli explained everything, okay? The spin's internal structure, mathematics, and everything he explained. Okay. So Stern-Gerlach experiment, I didn't actually give you all the details of the experiment. So let me explain this, and it's about, okay, we have 8 minutes to go, so it's right on time. So let me explain actually what the experimental results they got. So first of all, they get half and half, okay? Half and half island, all right? And then let me call that direction of putting the magnet as a z-axis, okay, z. So they put it on z-axis north and south pole. They got half and half island, okay? They thought, okay, it's fine, we got half and half, they're discrete. Let me call that experiment you saw, okay, that shooting silver and then passing through the magnet as I'll call that Stern-Gerlach box, okay? So that yellow box. So, and then I always put Z, okay? Z to represent magnet is along which direction. Okay, so SGZ box, you get half and half. So this actually allows you to think, oh, this quantum system actually have a Hilbert space dimension of 2. Okay, so you remember what is that? Particle in the box has infinite dimension, right? It has infinite dimension. What is that? Harmonic oscillator has infinite dimension, but spin is quite nice. It's a finite dimension. It has only 2. Okay, it has only 2. It's the simplest possible quantum object. It has 2. Yeah, Hilbert space of 2, and they're discrete. So any quantum state in that space, you can actually think of it as it's this form. Okay, Z up, Z down. And then you can put some arbitrary coefficient. That's it. Okay, there's no other quantum state other than this form. It's a very nice two-dimensional Hilbert space. Okay. Now, what do you get? Okay, so now you can do this experiment. You have got half and half there, well split. Okay, it's possible to some box blocking all the silver atoms, and then rest of the 50 to go. And then you repeat the exact same box, okay? If exact same experiment, cascade them, do experiment again. What do you get? Well, nothing surprising, okay? You only select spin up, and then they all become spin up, okay? So, okay, there's nothing surprising here. Okay, this is okay, acceptable result. The surprise comes from here, okay? The weird things coming from here. Now you have this box, the same box, you get like only spin up in Z direction, but actually you can put another box that is SGX, okay, not SGZ. So what I mean is that, so previously you have this N and South Pole like this, you rotate it like this, okay? And then left and right from the silver atom's perspective. It felt the force up and down, pass through, you only filter half, spin up, and then now it's this left and right force, okay? So if you do it, what happens? It turns out that, again, they are split into 2 islands, left and right, but this time you are measuring x-axis, right? So this is spin x up and down, all right? So you only selected spin z, z-axis spin up, okay? Only up. And then you do x-axis spin measurement, you get half and half, okay? So quantum mechanically, you can think of it as they have an overlap, okay? Z spin up and X spin up has a non-zero overlap, and you measure it, okay? You have a spin X up and Z up and X down, you have non-zero overlap. This is actually a little bit counterintuitive for classical thinking, because the classical thinking is what? It's just a vector, okay? Magnet is like a vector, so you put magnet like this, and then those two vectors, geometrical inner product is 0 actually, right? It's not 0 here. Okay, z-axis like quantized actually means the North Pole up, North Pole down, okay? That's classical thinking. X-axis is North Pole this direction, North Pole that direction, and you feel like, oh, well, looks like they're orthogonal. Like, they're not, okay? That's the structure of the spin, and then that's why it took a lot of time to figure out what really is going on for Pauli. Then there is another experiment. This is the highlight of a Stern-Gerlach experiment, okay? highlight is that, okay, now you can block off the result of the previous slide, right? So you only select Z up first, and then you pass through X up, okay? And then you feel like, okay, I filtered twice. First time Z up, second time X up. So it's kind of a, joint of these two conditions. So this electron must be Z up and X up at the same time. That's classical thinking. And then turns out that then your classical thinking will tell you that, okay, if my thinking is correct, if I put Z box again, it's like a filter, right? I'll only have Z up only. That's what you think. Turns out that you get half and half again, okay? You previously filtered in the first stage, filtered all the Z up, and then next stage, you filtered X up only, and then third time, well, not just this previous step, but actually the step way before, I already did the filtering of Z up, so I will get Z up only, but that's wrong, okay? Because you did this action of you sandwich this SG box in the middle and filter out only spin up. Because of that behavior, once you start measuring Z, right, it's going to have both, okay? And then proper interpretation of this is that the moment you measure, right, SGX up, okay, that now your quantum state has collapsed into spin X up state, okay, spin X up state. And then this spin X up state is in fact superposition of a spin Z up and spin Z down state. All right, and then it explains everything. Spin Z up state is also a superposition of a spin X up and spin X down state. That's why you get a 50% in the second stage. Okay, but once you filter out, right, spin X up is a superposition of a spin Z up and spin Z down. So you will see that mathematical structure in the next class. Okay, let's finish here.